Hey guys, in today's video I'm going to be discussing proof by contradiction. So this is another proof method. We've already seen proof by induction and proof by strong induction. So let's get into this. So we have reached a contradiction if we have shown that a proposition Q and its negation that's not Q are both true. How can Q and not Q both be true? This is not possible. So if we end up reaching this case, that means we reach a contradiction. So to prove a proposition P by contradiction, we assume that not P is true. So we have to assume that not P is true and show that under this assumption, we reach a contradiction. So let's look at an example for this. Given sets A and B, show that A and B, or A intersection B, and the intersection of that with A excluding the elements of B is equal to the null set. So you have to show that these two are equal. So a direct proof might be your first thought, but it doesn't really seem possible. So if you wanted to do a direct proof, you'd have to take an arbitrary element that belongs to this part right here in blue and argue that because it belongs to this, it belongs to the null set. And that doesn't really seem to make sense. How would we even prove that? So let's look at it in terms of proof by contradiction. So for the sake of contradiction, you have to assume that not P is true. So what is not P? It's this, but it's just not equal to the null set. So if A intersection B intersection with A without B is not equal to the null set, this is the contradiction, and we have to assume it's true and then move on. So by the definition, this means that there's some element X that belongs to this. So if X belongs to this, that means X belongs to the first part, which is A intersection B, and X belongs to A without B. So this is by the definition of set intersection. So since X belongs to A intersection B, we can conclude that X belongs to B because this includes the elements in both A and B. Similarly, for this, since X belongs to A without B, we can conclude that X does not belong to B. However, these two statements are a contradiction. Our earlier proposition is incorrect. So since we reached a contradiction, we know that the proposition P is true, or in other words, A and B intersection A without B is in fact equal to the null set. And the way we prove this is we assumed its negation. Let's say this is proposition P. We assumed its negation is true and showed that under that assumption, we reached a contradiction. So that's how simple proof by contradiction is. If you guys have any questions, make sure to leave it in the comment section below. Thank you so much.